March the 3rd. And our presenter is Professor Steve Pekarek at Purdue University. And anticipating the weather, among other things, we anticipated that he could do this remotely. We used to do this routinely, and of course, all the software's changed, so we have to get back into it. But I'm very much appreciative that he's joining us this afternoon. And as you see, he's presenting some magnetic equivalent circuit work related to wound rotor synchronous machines. We as a group, and by that I mean mostly Purdue with some work at Illinois and some other places, have done a lot of different magnetic equivalent circuit modeling work for machines. Relatively efficient compared to finite element, but you trade off certain levels of precision in terms of much faster, simpler models. So, Steve, I think you can go ahead. Welcome.
Thanks, Phil. I appreciate it. Thank you, everybody. I'm sorry I wasn't able to join you, but I'm certainly grateful that you had asked, and it's always a great opportunity to share some research. The topic that I'm going to discuss today, as Phil had indicated, is magnetic equivalent circuit modeling for the design of wound rotor synchronous machines. It seems like this was started from my end only a couple of years ago, but I realize how much time has changed, and it started probably over a decade ago for me, and it's been progressing through a sequence of students, great students, Hamza Durbis, Michelle Bash, and most recently the work I'll present today was in collaboration with Ron Wong and the contributions he made. And so with that introduction, I'll go to slide 2 if you can. On slide 2, it describes really, if you look at this, the pictures of what's been most recent on our mind, and that is on the left-hand side and on the right, you'll see the wound rotor synchronous machine, but they're connected to power electronic circuits. In numerous applications now, there is an interest in having DC as the distribution type. And so you see VDC, and the conversion process from AC to DC, you could, as shown on the left-hand side, go use an active rectifier for the conversion, or alternatively, you could use a passive rectifier. And from a design perspective, we're trying to select the machines and choose geometries and material properties so that we can rigorously justify that we're optimizing the machines for their respective applications. The design variables I show there on slide 2, and if you look on the left and on the right, there's many that are the same. DRC, the depth of the rotor core, L, length, depth of the rotor tooth, G is gap, and that goes on and on. But then you start to see that there are differences between the two. On the left-hand side, shown in purple or pink, depending upon how you perceive that color, you see a stator current amplitude and a beta, which is a phase relative to the rotor's position. And I show that below there, that IAS, because you have control with an active rectifier, IAS is some amplitude cosine of the rotor's position plus beta. On the right-hand side, you don't have that capability. Your field winding will provide a back EMF. You'll use that to regulate VDC, but you have no control, direct control of stator currents. And so the variables there change, but in addition, you get some new variables. And really to look at those new variables relies on the fact that you know that the DC voltage that is present on the output is a function certainly of the field current that's setting up your back EMF. But if you talk about what inductances are going to dominate when you're trying to figure out what DC voltage you'll get, it is the subtransient quantities, LQ double prime, LD double prime, and those quantities that those that look at synchronous machines and power systems know very well. The question, however, from a design perspective is, how do you establish what those are? How do you specify you should have a particular LD or LQ double prime? And to get to those points, what you're really trying to do is specify how do you configure damper windings. And so we have three variables that are shown there in blue, and that's the radius of a damper, that's an R, the number of damper windings, and then how you connect them. Do you connect them interpolar, or do you connect them between poles, or maybe a combination? And so those are the things that we are attempting to explore. If you head to slide 3, you'd say, okay, for the active rectifier, this is kind of a walk in the park. See spot run. You have on the left-hand side the geometry. There's your wound rotor synchronous machine that many people love, particularly those at Illinois and Purdue. The topology is shown. We have salient poles. We have the dimensions there that are shown. And the way we like to try to do our designs is based on the magnetic equivalent circuit. On the right shows the circuit for an active rectification, the one that we use. And the salient properties of this are, okay, we anticipate what the magnetic flux paths are, and we represent the ratio of a magnetomotive force to flux using the reluctances. Our favorite variables, you have to use this variable if you love MECs, is R. You put them everywhere. You sleep at night and you dream in R's. Except when you get to the windings, you can call those by their names with currents. And then what we have tried to do is structure our MECs so that we solve it using Kirchhoff's voltage law. We use fluxes as our unknown. And in the past, we've shown that when you do this, you do not have to use any saturation factor to get numerical convergence. It's a very well conditioned solution, and so that's why we use that flux as our variables of unknowns. So in our design code for an active rectifier, we can decide all the pole pairs and all of these geometries, the number of turns and the materials of our particular machines, and an MEC is used to solve for that. If you head to slide 4, the calculations include torque. You'll note that it's not your standard QD expression for torque. Instead, it's expressed in terms of the derivatives of the permeance with respect to theta R. And so we have those expressions. We represent the resistive loss of all windings, the core loss in the stator and the rotor, and that includes hysteresis and eddy currents. And when we're doing the active rectifier, we also include the conduction loss of those devices. We have not included switching losses yet, but we do include conduction loss of our devices. And so when we calculate loss, we include the combination of all three. Are there any questions at this point that anybody would have? Okay, I'll proceed to slide 5. And when the passive rectifier is considered, the figure changes. If you think back 2 slides and you say to yourself, "Self, what did that wound rotor synchronous machine look like?" And you looked at the rotor, you wouldn't have seen any of the holes here that you see here on the left-hand side of this slide. Indeed, we have holes that are positioned throughout the rotor body. And I'll have to establish that if you look, and it may be hard for you to see, although Kevin might be able to point to these, on the rotor pole body, where, for example, you have a WRP, those 2 holes are usually for structural purposes, to keep the laminations together. And so often manufacturers will include those. Those are not intended to be paths for damper windings, but we include them because of magnetic operating point. And but the other ones that are shown on the pole tip, those are. And the question becomes, how do you represent what changes in your magnetic equivalent circuit? And on the right-hand side, I've highlighted in green where the change takes place. You have some additional items. For one, you now can have current in those bars. And so as a result, you have MMF sources. And in addition, the dominant component in those subtransient inductances are actually the leakage paths of your damper windings. So if you look close, those R's, the reluctances that are in green, show there's an RRL, and then there's subscripts to denote their position, but it's just that RRL. The RRL stands for that leakage, the leakage that is occurring around each damper winding. And the provisions that we have included within the model is to state you can place these damper bars arbitrary number at an arbitrary position and each get an arbitrary diameter. And so that sets a number of degrees of freedom to explore, quote, optimal designs. If we move to slide 6, I'll be a little bit more specific about how we include the reluctances within our MEC model. What does it look like in terms of our flux paths? And I'll point your eye in this slide first to the left-hand side on that rotor pole. There's some variables. RRTE1, that stands for the reluctance of the rotor tooth, the end section. Next to it, RRT01, that's a rotor tooth and outer section we labeled 1. And this is where, for this example, we have presented our first damper hole. And the first thing we do to calculate the damper effect is to include it just magnetically without any damper current. And in the end or those outer sections that are not directly above the rotor pole body, we represent that flux moves tangentially from left to right. You can kind of see that in the arrows. And it's going from the left, and then it's leaving that section to the right. And we use an expression. We, in essence, take that geometry and use that geometry to calculate a reluctance that is shown there on the right-hand side. For the damper bars that are directly above the rotor pole body, we assume that the flux is moving directly vertically into the rotor pole. The expressions are very similar, and so we have expressions for inside the rotor pole body and outside. And the expressions are shown here on the right-hand side. On the slide 7, I'll just denote here the salient point that now when we have our respective active dampers, we also include a parallel path, and that parallel path is the permeance or the leakage that can occur. And the leakage includes permeances on this slide P1, P2, and P3. And those are permeances that are associated with the damper across the damper bar itself, external to the damper bar but not hitting the air gap yet. And then permeance 3 includes the respective air gap. And so we have expressions that are derived for those, and we combine those together in a parallel set. Okay. We'll move on to slide 8. And within our design codes, what we have included is the provision to, as I had indicated, have arbitrary damper bar numbers. And the way we have structured it, when we have an odd number of damper bars specified, we position one of them centrally across, just above the rotor pole body, and the rest of them are distributed outside in the respective outer edges of the rotor pole tip. If there's an even number, then there is no damper in the center, and instead they're just distributed out on both left and right hand sides. They're symmetrically distributed on both sides of the rotor pole. And we also then include, as part of our design code, a vector that specified what is the radius of each of these damper bars. And we can also adjust the vertical height within the pole by using a scaling factor that's used in our design codes. So that kind of sets up an idea of what we're doing in terms of the MEC model statically. I'll now proceed on first by setting up in your mind what is a static MEC model, what are your knowns and unknowns, and then heading away from that toward our dynamic model. If I was giving this as a lecture, I'd probably pick on somebody in the audience right now and say, okay, when you have your MEC model, what are your knowns and unknowns? But I'm not there with you, so I can't do that. Instead, I'll just state it up at the top, system of equations. What are you attempting to do if you just had a steady state model? Well, it's A times phi equals F. And your A is your system matrix. It contains your geometries, your reluctances. Your phi is all your loop fluxes. And your F is standing for what you might think the MMFs. The MMFs of your stator and rotor. The field windings, the stator windings, and your damper windings. And I show these in terms of mathematical entities. If anybody's interested, I'll point you to the paper where we describe this. I'll just focus your mind today, however, on A phi equals F. That's how it's initially structured for the steady state model. If we move now to slide 10, on the top sets that steady state model I just described. The way it works in the design code is we specify winding currents. Those are input. They form your MMFs, and then you solve. And the phis are the output. That's the block shown. And then you post-process. You get your lambda, your flux linkages of your ABC windings, your field winding, and you can then solve for your voltages as desired. But where we're going to head now, and in the next few slides, is we restructure that model. We're no longer in steady state, but instead we are dynamic. And so the way we've structured our dynamic MEC is we have winding flux linkages as our input to the MEC. The MEC then solves for currents. The currents are then used to external circuits to obtain the voltages of the respective windings. The voltages are used as an input to numerical integration to get the winding flux linkages, and the circle continues. And so that's our specified loop. If we now move to 11, slide 11, this shows kind of the general way in which we went or go from a steady state model to the dynamic MEC model. We have some specific steps, and in essence those steps are we first rewrite the static model, the steady state model. We define flux linkages in terms of our respective loop fluxes. That's kind of the second step here. And we've worked out the algebra for how that works with our dampers. So in the middle of the slide is lambda damper pole 1, lambda damper pole 2 and 3. In terms of phis, those are loop fluxes. And then we start to form our dynamic MEC system of equations. And so the progress has already started here where you're seeing currents on the left-hand side, IABCS, I damper pole, and phi. Those are some loop fluxes as well. We'll progress on to slide 12. And on slide 12, it just shows the continuation of this process where we, in our model, we go to a QD frame of reference. So we take our transformation of our ABC currents, and also our ABC flux linkages. We express it in terms of those quantities. We scale quantities so that our matrix is well conditioned. And then we proceed on. And I'll show how we proceed on slide 13. The process that we do to proceed on is now to establish our state equations, where we need our flux linkages, or our derivatives of flux linkages in terms of currents. And we use Ohm's and Faraday's law, where P here, P lambda dP equals TdP IdP. I is the currents of the dampers. P is the heavy side notation for d dt, and lambdas are our flux linkages of our damper poles. On slide 14, we show something similar to what you've probably experienced. Is we now have our derivative of our stator windings, lambda QD0S equals VQ0D0S minus R IQD0S. So in essence, Park's expression. We calculate resistive losses, and that includes the stator and field and damper windings. So that's our overall system model, where we have lambdas as state variables. We integrate those, solve for those, hand those to our MEC, and our MEC must obtain the currents of our respective windings. So I'll show on slide 15 some of the hardware validation that we've done, and to validate our models. This is a geometry that was made for us by an industry partner, and they had actually 5 damper windings placed on the top of the damper pole, or the rotor poles. Those are shown. There's also some structural holes. Those are not, damper bars are not placed on those. Rather, just steel connections are placed within there. And the bottom left and the bottom right show on the bottom left is the assembly with the stator, and the bottom right is our rotor. And you can see on the left-hand side of that is the field winding, the brushes for the field, or the connection for the brushes for the field winding. Okay, in slide 16, we show some open circuit voltage measurements, and you can see we compare them MEC versus hardware. On the left and right, those are time domain waveforms. And on the right-hand side is, in essence, our saturation curve. We energize the field winding with the rotor spinning at 1800 RPM from 0 to rated field current, and then obtain our line-to-line RMS voltage. Interesting thing about this, on the left-hand side, you may say that looks like it's not a sinusoid. I mean, if you wake up early on a Monday morning, you may be able to convince somebody that's still halfway asleep that that's a sinusoid, but in practice, you can, by now in the day, you'd say no way. And it has a lot of slot harmonics, and it also has some back EMF harmonics. And the reason for that, we're testing our codes in worst case scenarios. And so neither the stator nor the rotor was skewed to try to eliminate those harmonics. And it was also it wasn't a sinusoidally wound machine. It was more toward a concentrated winding machine. And so it is harmonic laden. And despite this fact, the MEC predicts the waveforms quite well. On slide 17, we show some results now when we connect the machine. And here the manufacturer took our machine effectively and put it on their standard industrial load testing that they use prior to shipping their product. And so this is a 10 kilowatt unit, and the loads were varied from light load to heavy load. Light load is shown as 1, heavy load 4. The output powers ranged from 3 to 10 kilowatts, and we were testing first our torques, our output powers predicted, our phase currents that were predicted, and then probably the more important points are the total damper and core loss. And I'll let your eyes glean to that. I'm looking now at the second table where it says under the MEC P core plus damper, and then the test of the power of the core plus damper. And that's where we were really trying to get the numbers correct, or hopeful that the numbers would be correct. It would represent some figure of merit that our core loss was being predicted well and our damper loss was as well. And you can see from those numbers that we were very close in both. And so we were quite pleased with the fidelity of our model for an arbitrary geometry that was selected off of a Pareto front. If we move now to slide 18 also, I'll just show this is the voltage waveform, not open circuit voltage. Now this is at full load. Here is the MEC versus the test. And again, you can see the harmonics that are present, and the MEC predicts them reasonably well. And so our total RMS error is approximately 5%. And this machine is in very heavy saturation at full load condition. We'll go to slide 19 now. And this is where we were testing standstill frequency response test. And Pete, I can leave it to you to quiz the audience on what this means in terms of Q and D axis damper windings. I don't know if you guys cover that, but in a standstill frequency response test, your dominant Q and D axis, LD double prime and LQ double prime, are the high frequency asymptote of your operational impedances. And so that's a motivation for us to explore the standstill frequency response test. And you know, this is showing this remotely is kind of tough, but I'll first highlight there's a black figure there with squares, and that is the test D-axis operational impedance amplitude. It starts at a value of roughly 3 times 10, so 30, and it drops down. It starts dropping down at less than 1 hertz, and it continues on down and reaches an asymptote at roughly 100 hertz. You're relatively flat. And shown on these also are a magenta and a blue, and it's the light blue in this case. And you can see these are the MEC and a finite element model of the that is trying to predict those values. And the D-axis is pegged very well. There are some differences which you might expect just due to resistances that are slightly off and leakage paths that are not quite exact, but for the most part these are predicted quite well. The Q-axis has more error, and the Q-axis, what we had found was when the manufacturer had installed this, they had inadvertently placed an additional path of Q-axis flux that's hard to model. And it's also hard to describe that remotely. So I'll just highlight that the error in our Q-axis model between MEC and hardware is mostly due to a serendipitous path. But when we compare it to FEA, the comparison is actually quite good. So I'll highlight that a little bit more here on the next two slides. And on slide 20 is just when we've adjusted the depth of damper bars in our model and we've compared the results with the finite element. This is a cleaner plot, and you can see Q and D axis here, MEC versus FEA. And here's on the left where we put the damper bars pretty deep into the poles. And on the right is an instance where we put them very close to the surface of the poles. And so you get different responses depending upon that. And it turns out when you put them very close to the top of the poles, that most of your leakage is going to be accounted for in the space between the respective damper rotor poles. And that leads to, that's a relatively difficult place to have an exact MEC representation. It's in air, you're getting fringing, and so you'll see, for example, on the right-hand side, as you reach a high-frequency asymptote, there is some difference between the FEA and the MEC Q-axis subtransient inductance, but it's relatively minor. And so we're quite pleased with the MEC model. Okay, now I'll just show an example design study where we were just interested to see if we were given the task of designing a 25 megawatt machine and you had to select, should you use an active rectifier or should you use a passive rectifier, and what would happen in both those instances. This was a design study we did just for fun. And the results are shown on slide 22. And this describes what's so-called the Pareto front. It is the design trade-off space. We have, in this case, two respective desires. We want to minimize the loss from our machine / converter as a combination, but we also want to minimize the overall mass of the machine. And so this represents the fronts for those respective designs. The red is the wound rotor synchronous machine / passive rectifier. The blue is the active rectifier. And the front is not one design, but it's the family of designs that represents the trade-off between, again, loss and mass. And so two things that are of interest here. The first is, which one wins, the active rectifier or the passive rectifier? The initial thought would be, well, I should be able to win with an active rectifier because I can control my stator currents. Because I can control my stator currents, I do not get the harmonics due to rectification. And I can effectively achieve an maximum efficiency if I'd want to with my stator currents and my field current. Whereas in the passive rectifier, you don't have control of your stator currents. You have to accept what you get. They have strong harmonic content. And so you wouldn't think you'd have a chance to beat the machine. The active should win. But in fact, what we found, interestingly, was the passive rectifier system generally had less loss. Let's just look, for example, select a mass on the x-axis. Select one that's 10 to the 4th. So I'm at the number 1 there, and I head up, and the first one I get is my red curve, which would show 2 to the 5th watts of loss. So 200 kilowatt loss on a 25 megawatt machine. And if I look at my active rectifier system, I get 240 kilowatt of loss. And so there is a difference there. And why is there a difference? And it turns out when you explore this, the key difference is when we have our IGBT, which we have to series and parallel tie to get suitable device ratings, compared to diodes, which we also have to configure so that we get suitable device ratings. The diodes have a lower net on-state voltage. And so we chose these from commercial products, and so that is the dominant difference in that loss, is those on-state voltage drops, the reason. Now, I say that there's two interesting things. The second thing that was interesting, I'll actually go to slide 24 first, and I'll show figures on the left and the right-hand side. On the left is a representative machine off of the Pareto front of the active rectifier system, and the right is one off the passive rectifier system. And here's where the interest came in. There are no damper bars. They all got closed in. The radii went to zero. That the GA, as part of our optimization process, we utilized a genetic algorithm, and they all closed. There is no need for them. And if you go back now to slide 23, we start to see here are our respective genes. And what tends to happen is, depending if you have active or passive rectification, your geometries, your number of turns of the stator in your field, they change. They're different. The machines adapt according to the constraints that are provided by those respective topologies. And they've adapted in such a way, and we've run this study many times now, that for some reason they've selected so that the loss of those damper bars is not particularly good, and so they eliminate them. And the number of turns here, the reds on this plot, on all of these plots, are the genes of our passive rectifier. The blue are those of our active. And if you're interested, I can go through or point you to the paper where we describe each of these. I'll highlight just the pole pairs, which are on the left-hand side, P, capital P with a lower subscript p. And you can see, for the most part, if you look at the red, there are two pole pairs, so 4-pole machines. In contrast, in the active, the GAs have selected over many generations either 6 or 8-pole machines. And similarly, the air gaps are different. If you look just up to your right, G in meters, it shows the respective air gaps. And as a group on that Pareto front, the passive rectification systems had lower air gaps than that of the active. So I will conclude now. This kind of shows where we've been heading with the dynamic MEC model, comparing the respective topologies. We have the MEC model that includes damper bar dynamics. We can have an arbitrary number of white damper bars placed arbitrarily in this within the rotor pole. We can connect inner or outer pole. It enables us to explore multi-objective design of machine/passive rectifiers, and it's readily extended to multi-phase machines 6, 9, 12. And we've performed an initial study of passive versus active rectifier systems, and a surprising result is that we found that machines from the passive designs tend to be less massive for a given specified loss. That was for very high power systems, and right now we're working on some that are lower power and doing a comparison of that. So with that, I will conclude, and I'll open the floor to any questions.
All right, thanks. Okay, questions from this end?
It's not a question, it's just a comment. I was listening to you in the beginning, and I thought you said this was a round rotor machine. So I was surprised to see that big dog bone configuration, and you said wound rotor, not round.
Yeah, that's right.
Very, very interesting talk. I enjoyed it, and I love those characteristic impedance graphs.
Yeah.
Yeah, that would be probably XD on the left and then XD double prime on the right.
Correct.
Yeah.
That's exactly right.
That's really nice.
Thank you.
And we could do this by the way. Anybody else? Yeah. Professor Haran.
Hi, Steve. This is Kirupa Haran.
Yeah.
Good talk. Quick question. I mean, what are some of the main applications where people are using wound field synchronous machines with, controlled rectifiers?
Yeah. So on aircraft power systems, for example, that is one where people have proposed to utilize that. So they're converting AC to DC and doing that with an active type of system. The Navy has been exploring it for their respective next generation ships. And actually, there was a question raised in the literature several years ago, and it goes around the idea of this. The Navy is considered DC power for a number of reasons. One is just cable size and cable weight. People have shown that there's a reduction that can be had with DC versus AC, and there's other reasons. But there was a paper put out, actually Steve Lieb put it out, from MIT, in which he said, it's crazy to consider these DC systems because you cannot do passive rectification. The machines would just be too large because you have to deal with all of the harmonics. He said, so you're going to have to go to active rectification, but that's also insane because of maintenance-related issues of having to deal with, if anything breaks while you're at sea, you're never going to be able to repair this in situ because of the complexity. Plus, you have your rotor position sensor, etc. So the Navy was interested and remains interested in active and passive rectification. And this kind of shows that the conventional wisdom that you could not use passive rectification is probably, in terms of, because it's lead to a large machine size, is probably not correct.
All right.
So that was a long-winded answer. I hope it helped.
Okay. Other questions? I have one. One thing you didn't quite make clear is what is the operating point dependence of the trade-off? I mean, you showed the various designs, but you sort of implied it was at one particular operating condition.
Mm-hmm. Yeah, in most of these, the geometry, if you have a fixed speed design, what you can do, if you have just one respective speed, which we were considering initially, you could say, for example, Phil, well, let's average our losses if we know the cycle of our respective system. Let's just take an average of those as part when we create our fronts. And then you create a design space in which your average is optimized compared to your peak. And we've done that in both ways. where we just consider our maximum operating condition and assume that it's on at that 100%. And then we've also done weighted averages of less than that. And what we tend to is the fronts, you don't get any better designs in going to, your design space is really dominated by what's happening at your peak condition. And so doing that weighting has not led us to superior machines. And so at least for fixed speed. And so fixed speed, we have that single operating point. And I characterize that just for wound rotor, that's our experience as well.
All right,
So,
thank you.
Yeah.
All right, any other questions? All right, let's thank our speaker again. So we really appreciate that. I hope you guys were missed by the same snowstorm that missed us.
Yeah, we were.
And yeah, that's good. You're not snowed in either. So sometime we have to get together in person as well. But it actually worked quite well at this end. So we very much appreciate it. Thanks a lot.
Thank you.
All right. Goodbye.
See ya.